Hi guys, this is George from Hardware Electronics, and this is the second video in a two-part series on the CAN bus. In the first video we took a look at the physical aspects of the CAN bus and also the CAN bus protocol itself, and in this video we're going to move on to a real-world example of how to use the Hardwire PDM to read data from another device on the CAN bus. So I happen to have a Fueltech ECU here with me. So that's the device that we're going to be using to send data to the Hardwire PDM. But the method I'm going to show you today to figure out how to read the data from the CAN bus can be applied to any ECU manufacturer. All that you need is a datasheet with the CAN bus output stream documented. So the first thing to do is to actually make sure that we can see data being sent from the ECU to the PDM. So on a Fueltech device, it's quite easy to set up the CAN bus output stream. All that we need to do is go down to the CAN bus section in the settings and make sure that send broadcast data and send fixed packet data is enabled. And once you've done that, that's everything that we need to do. We can write this to the ECU. So that's everything that we need to do in the Fueltech software. Now let's make sure that we can actually see data being sent from the ECU to the PDM. So we can close this off and now open up the Hardwire PDM configurator software. Like always, we'll connect to the PDM and then we'll go to the configuration tab, and we know that Fueltech happens to send its CAN bus data at a CAN bus speed of 1000 kilobits per second, so we'll just select that here in the CAN bus settings, and straight away before we do anything we can press send on this and then go over to the monitor tab and look at the CAN bus analyzer, which is a new feature we've added in the latest software revision. Press start and you can see straight away that we're getting CAN bus data coming in from the Fueltech. I should mention as well that the Fueltech and the PDM are the only devices on the CAN bus, so all of this data is coming from the ECU. Now we can click fixed view here, and this will show us all the different CAN bus IDs that are being sent from the Fueltech. Now the Fueltech sends two types of data. It sends fixed packet data and it sends segmented packet data. Okay, so I just wanted to interject and tell you guys about what segmented packet data is. So normally when we have a CAN bus message, the variable data will be stored in all of the data bytes. So we might have something like this. We might have byte 0, 1, 2, 3, 4, 5, 6 and 7, which is the data bytes in our CAN bus message, and then the actual data variables which we're sending will be inside of these bytes. So you might have a 16-bit data variable, so here you might have your TPS value, here you might have your map sensor value, here you might have your coolant temperature, and in this 16-bit value here you might have your inlet air temperature value. And you can see that all of the data variables take up all of the data bytes inside the CAN message. And at the beginning of the CAN message we obviously have our ID. So we have our ID here at the beginning of the CAN message. But what this means is that this CAN bus message ID is now taken up by this data format here with these four data values inside. So let's say that this is an ID of 0x012. These are now the data variables which will be associated with this CAN bus ID. So now if we want more data variables, say that we want here our gear position, maybe our lambda, maybe here we want steering angle, maybe here we want our speed. So to transmit these data variables we need another CAN bus ID. So this might have an ID here of 0x013. So as you can see, the more data variables that we want to transmit, the more IDs we need to use up. And there's a few reasons why this might not be a very good idea. In most situations this is a good idea. It makes it very easy to understand and the format is very nice to work with. But in a lot of physical hardware, such as the Hardwire PDM, for example, you only have a fixed number of CAN bus message filters available to you, which means that you can only filter out so many CAN bus message IDs before you run out of CAN bus filters. And that can then limit you with how many data variables you can get off the CAN bus because you run out of CAN bus filters. So a way to get around this is to use what's called segmented packet data. And with segmented packet data, we just use one CAN bus ID, and instead of having the data variables take up all of the data bytes, we now reserve perhaps the first byte for a message ID, like this. And then here you would have your data variables as before. So this could be your TPS. This could be your inlet air temperature. This could be a map sensor. And then you might have 8 bytes here at the end. Maybe you could use this for your gear position. And what you have now is a message ID at the beginning taking up the first data byte of the CAN message. And the message ID can vary between 0 and 255. And so now instead of having only 8 data bytes for each CAN bus message ID, we can now have 255 multiplied by 7 data bytes just for one CAN bus ID. And so now, for example, okay, so the first message ID here might be 0, and then the next message ID might be 1, and then here you'll have some different data variables. So here you might have now your coolant temperature sensor, your lambda, your speed, etc. And so now you can go all the way from 0 to 255 in this first byte, and you have many more data variables available to you. The downside to this, of course, is that you need more complicated software which can now filter out not just on the CAN bus message ID but also on the first byte of the data message as well. And the Hardwire Electronics PDM can obviously do this, but in this video we're just going to focus on the first scenario, which is fixed packet data, where one CAN bus message ID is responsible for, say, 4 data variables. The actual data that we're going to be looking at today is down here on page 161. It's in this table here. And you can see from this table that we have 8 different CAN bus IDs, starting from 600 going all the way up to 607. And each CAN bus ID, each CAN bus message, has 4 data variables within its 8 data bytes. So straight away we have 2 pieces of information here which are important to us. We have the CAN bus IDs that we need to look at, and we know that the DLC, which is how many data bytes are in the CAN bus packet, we know that that is 8, because all 8 bytes are filled up by these data variables. I should also just mention as well that this is a Fueltech 550 ECU, but the same would go for any of these other ones. It doesn't really matter again for this video. I'd like this video to be ECU agnostic, in the sense that you could take this information, go to another ECU manufacturer, look at their datasheet, and then apply exactly the same methods to read their CAN bus data on the PDM. So let's just check now that we're seeing these CAN bus messages come through. So these are extended CAN bus IDs, which means they're 29 bits long, which is why they're a little bit longer than the IDs we were looking at in the first video. And you can see that they start from 1408 0600 and it goes all the way up to 1408 0607. So if we go back to the Hardwire software, you can see straight away that we have 1408 0600, 601, 602, 603, 604, 605 and 606 and 607. Now the order that the CAN bus messages are shown here is just because of when I clicked on fixed view here, that's the order that the CAN bus messages came in. So now what we want to do is set up the CAN inputs on the PDM to read this data. So the first thing that we can do is look at the IDs, so 1408 0600. We can go to the configuration here, go to CAN inputs, and we can set up a CAN filter to filter out the CAN bus IDs that we want. So I'll come back here just for a second and I'll get our programmer calculator up on Windows, and we can type in hexadecimal here 1408 0600, and then we can go back to the configuration, to this CAN input, and we can now type this in here. 070-144. And you should see there in hexadecimal that's 14080-600. Now we have 8 different frames here, going from 600 all the way to 608. And you can see here that these IDs are consecutive, so they follow on one after the other. So in the Hardwire software, we can either input the individual IDs into separate filters, or we can just use one filter and select the number of frames that we want to read from this base ID. So I've selected 8 frames here, and what this will do is it will filter out all of the IDs starting from 14080-600 all the way up to 14080-608. So 8 frames starting from this frame. So that should be our CAN input filter fully configured. Now we can set up the actual CAN inputs themselves. So the best way I've found to do this is to actually label all the CAN inputs first. So I'm going to do that now quickly. So we're going to be looking at all of the values in this table. Now just to keep this video short, I'm going to do the first 4 in this table, but the same would apply for all of the values in this table. So the first one, TPS, throttle position sensor, we'll write in here, TPS, then we have map, then we have air temp, then we have engine temp. So that's the first CAN message done. And in the fuel tech documentation, if we scroll up slightly, we come to this table here, and this tells us a couple of things. So we can see the first 4 data variables here, the throttle position sensor, the map sensor, air temperature, and engine temperature. And this table gives us the units for this value. And you can see that the units for the throttle position is in %. So I'll type that in. This isn't particularly important, but it just means that we don't get confused with the units. The second is in bar. And then we have degrees C for both the air temperature and the coolant temperature. Now the filter, we're using filter number 1, and we're using the first frame of the first filter, so we can leave this as it is. And now what we can do is go ahead and configure the CAN inputs for these data values. So first of all, we'll configure the throttle position sensor. Okay, and this is the screen that you'll be met with. So at the very top, we have message heartbeat. If you hover over the labels, then they'll give you a description of what this is about. So the heartbeat, we don't need to worry about. Message filter as well. This is for segmented packets, and we are just doing fixed packet data. All we need to worry about in this case is the CAN data at the bottom here. So the first thing that we have is payload size, and that is how many bytes are in the CAN message which is being sent. And as we saw before, if we scroll down here to our table, you can see that in this CAN message here, there are 8 bytes being sent with 4 data variables. So this is 8 bytes long. So if we come back to the Hardwire software and we make this go to 8, I will just point out as well that at the bottom here we have test data. Now this is here just to make your life a little bit easier. We can input values in here. We have some default values here of 0, 1, 2, 3, etc. And these just allow us to do a sanity check on how we are passing the data from the CAN message. The next thing we have is the byte offset. And in this CAN message, we can see that the byte offset for the throttle position sensor is going to be 0 because throttle position sensor starts at byte 1. So if we come back here, you can see that as we increase byte offset, this blue box here goes up and down. But we want it to start on byte 0 here. The next section is the data format. Now if I click this, you can see that there are 6 different data formats that you can select from. There's unsigned and signed 8-bit, 16 and 32-bit numbers. So for the Fuel Tech ECU, the information isn't particularly clear, but if we scroll up here, it says that values are always transmitted as signed 16-bit values in big endian byte order. So that gives us the information that we need. We can come back here and this needs to be a signed 16-bit, and the endianness is big endian. So the next thing I'd like to look at is data endianness. And what does data endianness mean? Well, as we just saw before, we want to send our TPS value using 2 bytes. Okay, and in our first byte we can store a value anywhere from 0 to 0xFF. Okay, and in our second byte, I'll just do this in a second colour for reasons which you will see in a minute. In our second byte we can store a value from 0 to 0xFF, just like the first byte. Okay, so how do we get our 16-bit value out of this? Well, we can have what's called big endian or little endian. And the endianness basically means how do we concatenate these two values together to get our 16-bit value. Well, in big endian, we take the first byte first and we concatenate the second byte onto that. So the result would be 0xFF, and then the second byte afterwards, FF. And in little endian, the byte order is the opposite. So it's 0x, and then the first byte, FF. So that's the difference between big endian and little endian. It effectively tells you which way you concatenate the 2 bytes together, that is, join the 2 bytes together to get our 16-bit value. Next we have the bit position. Now as we increase this and decrease this, you can see that it moves along. In our case this needs to be 0, and the bit count underneath, that needs to be 16. 16 bits for our 16-bit signed data. So now you can see that the blue boxes, which is the data that we're going to extract from the CAN message, covers 2 bytes, the first 2 bytes in this case. And you can see that the raw result, which is how the PDM will pass this test data, is 0x0123, which is 0x01 concatenated with 0x23. And the result of that in decimal is 291. Now this is the raw result of the binary data. We need to scale and offset this data so that the data variable is in the correct format. Okay, so I'd just like to take a look at how data is actually sent over the CAN bus. Well, say that on the ECU we have a throttle position sensor value of, say, 24.5%. How do we send this value of 24.5% to our PDM? Well, as we know, our CAN messages have the following format with an ID and then some other stuff here, and then we also have 8 data bytes here. And then there's some other stuff as well at the end of the packet. So our data bytes are split up into 8 individual bytes. So our data bytes go from 0, 1, 2, 3, 4, 5, 6, 7. And on our FuelTech ECU, the TPS value was in the first 2 bytes here. So what does this mean? Well, that means that the TPS value is stored in a 16-bit value. And we know that in a single byte we can store a value anywhere from 0 to 255, which is 0 to 0xFF in hexadecimal. And in a 16, so this is for 8-bit. And for a 16-bit value, which is anywhere from 0 to 0xFFFF. So effectively we have 2 bytes concatenated together to get our 16 bits, or 2 bytes. So we want to send a value of 24.5, but all we can send is a value between 0 to 65,535. So obviously we can send a value of 24, that's not a problem, but how do we reserve the extra 0.5% at the end of here, the extra bit of precision? Well, in our basic 16-bit value we can't actually represent the 0.5%. So we have to do a trick, and that is to multiply this value of 24.5 by 10. So you have to multiply that by 10, and what that does is move the decimal place along to the right. So instead of 24 we can now send 245, and now we have the extra precision, actually stored in this value, 245. So we multiply by 10 and we get 245. Then we send this over to the PDM, and at the PDM side, that's where we apply our offset and scaling to get back to our original value. So in the FuelTech datasheet, you could see we have our value of 245 that's been received from the PDM, and it said in that table there is a multiplier of 0.1. So all we have to do to get back to our original value is multiply 245 by 0.1, and we get our original value of 24.5 on the PDM. So that's how we send floating point values, that is values with a decimal point, to another device over the CAN bus. We have to multiply it by a value of 10 or 100 or 1000 to move the decimal place along to reserve the extra precision that we would otherwise lose. So we go back to the documentation, come down to this table here, and you can see that for TPS we have a multiplier, in this case of 0.1. And this means that we need to multiply the raw binary data by 0.1 in order to get back to the throttle position sensor value, which is in percent. So we come back. Now the hardwire PDM can do a couple of things. It can change the decimal place, which is effectively dividing by 10. And you can see that now the adjusted result, which is the result after the scaling and offsetting, is the raw result divided by 10. So it's just moved the decimal place over to the left. And you can see we can keep doing that. We also have a multiplier underneath. So if I increase this, you can see that we're now multiplying the raw result by 2 and by 3, etc. And we also have a divider here as well. So we can divide by 2, divide by 3, and that divides the raw result. And then we also have an offset, which you can see here. And that's just going to give an offset of 4 in this case to the raw result. And you can also go negative with this as well. So in order to get the multiplier value of 0.1, what we need to do is actually divide by 10. So we put a division of 10 here, and you can see now that dividing by 10 is the same as multiplying by 0.1. And now our raw result is divided by 10, we get 29.1. So this is all the scaling and offsetting that we need to do for this data value. Then underneath we have timeout. If I just save this for a second and go back to the monitor tab, you can see that we are receiving data on this first ID here, 140800600, at a rate of, on average, between 1 and 3 seconds, I just saw there. So that's the period that the data has been sent. It's quite slow in this case on the FuelTech ECU. Now if we come back to the CAN input, so we know that the FuelTech is sending its data at least every 3 seconds on this ID. So what happens if 5 seconds goes by without us receiving any CAN messages? Well, if 5 seconds go by and we haven't received a CAN message, then we can assume that something has gone wrong with the CAN bus. And so the data that we have on the CAN bus we want to discard. We don't want that to be used by the PDM to do anything. So we have here a timeout value, and this is the maximum amount of time that we will allow to pass before we discard the value of the CAN input. So in this case we need to set this to a value which is higher than the maximum amount of time between the ECU sending data packets. So we saw a maximum value of 3 seconds between each data packet being sent. So we'll set this to 3500, this is in milliseconds. And now if 3.5 seconds goes by, then we will make this CAN input go to the default value. And in this case, we'll set the default value as 0. And this is a good default value for this data variable throttle position sensor. You can imagine that we're getting data from the FuelTech ECU of the throttle position, and let's say that the throttle is at 60%, and then all of a sudden the vehicle crashes, the CAN bus is broken, and we're not receiving any data. Now because the FuelTech is not sending any data anymore because the CAN bus is broken, we don't want the PDM to have that last stored value of 60 for the throttle position. We want it to go to a safe value, in this case of 0. So after 3.5 seconds without receiving any data, the CAN input value will go back to 0, which is a safe value to go to. So this is all that we need to do to configure the input for the throttle position sensor. So let's save that. And now we'll go onto the map sensor. We can do this a little bit quicker this time. So the map sensor value, you can see that that's in bytes 3 and 4. So we can do that now. The payload size is exactly the same for this CAN bus message. That's still 8. The byte offset now, because we're starting at byte 3, we need to go down like this. And the data is still signed 16-bit. It is for all of the data from the Fueltech. And the bit position we can leave at 0. And then the bit count, again, we can go up to 16 bits long. The data is big endian, like it told us in the datasheet. And now we can look at the scaling and offsets for this raw CAN bus data. So for the map sensor value, we can scroll up on this table again. And you can see that now we have a multiplier of 0.001. So this is the same as dividing by 1,000. So we'll go back here. And now we have a division of 1,000. And you can see our raw result here is divided by 1,000 to get our adjusted result. The offset we can leave as 0, and the timeout again, that's going to be 3.5 seconds. And a default value we can leave that as 0. So if there's any problems with the CAN bus, the default value will come into play and this CAN input will go to 0. So that's it for the map sensor. Now we can go back and look at the air temperature. We know that the air temperature here is in the 5th and 6th byte. So we can go back, and just while I'm here as well, I'll check to see what the multiplier is. And in this case, it's 0.1. So we can go back here. And for the air temperature, the payload size again is 8. The byte offset now, it's not in the first 4 bytes, it's in the 5th byte here, or byte 4 if we were 0 indexed. And then it's signed 16-bit. The bit position is 0. The bit count we can put to 16. Big endian. And we have a division of 10. The timeout of 3.5 seconds. And the default value we can leave as 0. Okay, so I think that's okay. And we can click save on that. And the coolant temperature, that's the same as the inlet air temperature. So this is 8. So the payload for this message is 8 bytes. Byte offset now, we're in the last 2 bytes of the 8 bytes. It's assigned 16 bits. The bit position is 0. Bit count is 16. And we big endian. And the divider in this case is 10. Timeout is the same as the other ones, 3,500, and we can click save on that. So now we have the first 4 variables extracted from this table. And just to test this, we can go back to the Hardwire software and we can press send on this initial setup, go to the monitor tab, and now go over to the CAN inputs. And you can see now that we're getting data from the Fueltech ECU. Now this Fueltech ECU isn't connected to anything, so some of the sensor values will be a little bit strange, but this looks like pretty sensible data to be getting from the ECU. And it looks like it's formatted correctly. So I'll quickly just go through the configuration for the second CAN bus message that the ECU sends. So the second CAN bus message is 14080601. And that sends oil pressure, fuel pressure, water pressure, and the gear value. So I will just type that in firstly like we did before. And now, instead of using the first frame from this CAN bus input filter, we're using the second frame. So it's 14080600 plus 1. So we're using the second frame. So the second frame here, we can select. And now we can configure these as we did before. So oil pressure in this case, if we go back, we can see that for all of these pressures, we have a multiplier of 0.001, which is a division of 1,000. So we'll go back to that. Again, the payload size is 8 bytes. The byte offset for the first oil pressure here, that's going to be 0. It's a signed 16-bit value. The bit count is 16 bits long. And we have a division of 1,000. And the timeout again will be 3,500 milliseconds and a default value of 0 we can leave. Save that. Fuel pressure is going to be exactly the same, so 8 bytes long, and instead of 0 byte offset we are offset by 2 bytes here. Signed 16 bits, a bit count of 16, and a divider of 1000, timeout of 3,500. Save that. So we have 8 bytes, a byte offset of 4, signed 16, a bit count of 16, and a division of 1000. Timeout of 3,500. Okay. Now the gear position, again 8 bytes, and it's going to be in the last 2 bytes. It's signed like all the data for this ECU, bit count of 16. And this value for gear, that won't have any offsets applied, so offsets are scaling applied, so we can leave this as it is, and the timeout we can put to 3,500. Okay, and press save. And this is the next 4 data bytes configured. We can press send on that. Okay, go back to the monitor tab, and you can see here that we're getting data again. Just to demonstrate what happens, I've also just disconnected the Fueltech ECU from the CAN bus, and you can see that the CAN variables now, they've gone to their default state which we set. Okay, so that about wraps up how to configure the Hardwire PDM to read CAN bus data from any device that you have.